Welcome to the Rutgers Experimental Math Zoom seminar. Today's speaker is Benoit Cloitre, who will speak about a heuristic link between divisor counts and prime densities in sequences. As usual, please mute yourself unless you have something to say. Please, Benoit.
Good evening, everyone. First, I would like to thank the organizers for the invitation at this talk, at this seminar, and to Doron in particular. It is a great pleasure to be here on the internet. I would prefer to be with you, but it's okay. Today, I want to present what I call a heuristic link between the counting of divisors and the density of primes within various arithmetic sequences. The central idea I will explore is that a simple ratio based purely on the divisor mass of the integers from 1 to n, or a sequence from u1 to un, can serve as a proxy for its prime density. We will see how this connection arises naturally.
Benoit, do you have slides? Right now we only have the title slides.
Sorry?
Do you have, right now we only see the title, the first slide. Did you change the slides, or it's okay like this? Do
you hear me?
Yes, we don't see any slides besides the first one that has a title.
Okay. The slide will come.
Okay, let's make sure, because sometimes people are not aware.
I have to click on the first slide and then to the arrow. Okay, it is working, but it is just the presentation. It is a fussy idea because we will see that there is no big, I didn't prove any big theorem, but it is based on observation and it is experimental. But it is related to many deep results on conjecture in number theory. So all began with what I call the arithmetic tableau. Perhaps many of you know this tableau, which was known to Euler, I guess. The first line, you have the integers, 1, 2, 3, 4, 5. The second line, every second integers. The third line, every third integers, etc. So you feel a tableau like that. It is an infinite tableau. And in the sequel, I will remove the 1 because they are not interesting from a divisor viewpoint. We consider only proper divisors. So you see this tableau has many interesting properties, very easy to prove, and which are well known, I think. First, if you take a number on the first line and you go to the southwest diagonal, you will meet all the divisors in order. So if we take 12 and you go on the southwest, you bump 6, 4, 3, 2, and they are all the divisors. So also we can look at the primes, because if you start from a prime, the same diagonal will be empty. We will cross nothing. So this tableau is very interesting because it gave many properties of number or of integer, and it is very regular. So I had an heuristic idea, which I call the divisor mass ratio, because I will take into account all divisor for all numbers from 1 to n. And we consider the mass S of n, which is equal to sum of 2 of m. 2 is a divisor function, number of divisor function, for m from 1 to up to n. And we define the divisor mass ratio. R of n is equal to n over S of n. So what is the heuristic interpretation? It is like a gauge to see how sparse proper divisors are in the arithmetic tableau, and it mimics the probability of avoiding a proper divisor hit when randomly sampling a field cell in the triangular grid below for n equal 31. So we see the triangle because you have some diagonal. And the interpretation of Rn is to avoid a proper divisor, so to touch an integer on the first line. So far, all is very elementary. And so a question arose because when we think to avoid any proper divisor from the set 1 to n, intuitively feels like hitting a prime because a prime has no proper divisor. So I had the idea to compare the divisor mass ratio to the prime density in the set of numbers. And the prime density is big pi of n equal pi of n over n, and pi is a prime counting function. And the question is very simple. Does this proxy predict the prime density? Do we have R of n, the divisor ratio, asymptotically equivalent to the prime density big pi of n? The answer is yes, because we know both sides are very well known. From the divisor side, it is well known that we have the sum for tau is asymptotic to n times log n. So the ratio for the divisor is asymptotic to 1 over log n. From the prime side, we have the Prime Number Theorem, which says that big pi of n is equivalent to 1 over log n. So we have a perfect match here. The divisor ratio is equivalent to the prime density. So the question here is it just a coincidence or a structural link? Because at first we have no proof that the divisor ratio implies the prime number theorem. Otherwise,
when I have a question, if you believe in the Riemann hypothesis, then you can get a much better asymptotic for pi of n, and possibly also for r of n. And do the match under the assumption of the Riemann hypothesis, or maybe the GRH?
So we stay at the elementary level.
Yeah.
Here, I think that the prime number theorem is elementary in nature. On Selberg-Erdos proved in 1949, I think, that the prime number theorem can be proved with elementary means.
Yeah, I'm just curious if there's any known better asymptotics for r of n under the assumption of the Riemann hypothesis.
Yes, here we're just concerned with the crude asymptotic, the first term.
Okay.
The Riemann hypothesis is for the remainder, and it is not the purpose, because I just want to point out that we have a correspondence between the first term, the first asymptotic term. Of course, there is no, in this talk, I have no, we can't compare the reminders.
Okay,
the
thank you.
structure, it is just at the elementary level, but we have a correspondence. You see the tableau is elementary, and the log come from elementary means, a discrete sum, on without a big
Okay, thank you.
machinery.
Okay.
But you will see later that we will be concerned with big problem in number theory, not the Riemann hypothesis, but batch conjecture and twin primes.
Thank you.
So here you see it's perhaps just a coincidence. So I decided to go further and to check it for sequences very important in arithmetic, like the arithmetic progression. You have u of k equal a times k plus b with a b coprime, and still we define s sub u of n equals the sum of divisors of uk, still the divisor mass, and the ratio is still r sub u of n equal n over su of n. So from the divisor side, we can prove that the sum of the divisor is asymptotic to phi of a over a, where phi is a Euler-Tauchian function, times n times log n. It is not difficult to prove. It is a known result from the folklore. And so we have the ratio here is a over phi a times 1 over log n. From the prime, on the prime side, we also know the prime number theorem in arithmetic progression from due to Dirichlet and after Hadamard. So big pi sub u of n here is also a over phi a times 1 log n. So here we find the correct factor between the two. And we have again a correspondence between the divisor side and the prime side. So at this time, I thought that it is not merely a coincidence. There should be some structural truth behind that. If we continue with simple example, we can consider to fix an integer m on a subset of invertible classes within the group Z over mz multiplicative group. And if we denote u of n be the first n integers lying in C, we have from on the divisor side, we have this equivalence. On the prime side, another one. And so if we consider C equal Z over M times Z, the proxy match exactly to. These are non-results. There is no conjecture. From both sides, we can calculate, we can evaluate the asymptotic. What is a conjecture is but the divisor side implied the prime side. I have no proof of that. But still, there is a correspondence which is striking to me, and which perhaps says something about the relation between divisor and primes. So after, when we check this phenomenon with other sequences, it still work, like u of k equal Betti sequence with alpha strictly greater than 1 on irrational, u of k equal k plus the floor of the square root of k, on many more examples of sequences. So I had a first conjecture after I will speak about the first conjecture. But before continuing, it is important to know that primes often occurs in sequence, but if you have no obstruction, so we need to put some condition on the sequence we are studying. And the first one is admissibility. No fixed primes divides all large value in the sequence. There is no obstruction that the sequence contains infinitely many primes. A moderate growth also. We need to have linear or polynomial growth for the sequence. If we take exponential sequence like 2 to the n minus 1, it doesn't work, but we understand why. We need a polynomial growth on some regularity, a stable distribution in invertible classes mod some integer m. But these are many sequences. The first conjecture is related to the first, the prime number theorem for integers you see before. For admissible regular sequences of moderate growth with stable local properties, I conjecture that the prime density equals the divisor mass ratio asymptotically. Here it always works. But if we consider different sequences, less regular, we have some bias appearing on the divisor side, on the prime side also. So the match is not perfect, but we still can compare things, and the interest to consider this kind of sequence is to try to understand, to tackle problem like the infinitude of twin primes, the Goldbach conjecture, we will see after. But for the twin primes, for instance, we can consider u of k equal the cas prime plus 2. So it is admissible, we believe. And we have a result on the divisor side. It is a Titchmarsh divisor problem. And we know that the sum over the divisors is asymptotic to a constant time n log n. So the proxy is here R sub u n asymptotic to 1 over a constant time log n. On the prime side, we have only a conjecture, the big conjecture of Hardy-Littlewood, which says that the prime density is asymptotic to a constant k sub 3 over log n. Is here k of sub 3 is 2 times the twin primes constant. The twin primes constant. So the scale is correct, but the constant differ.
Do you have a numerical approximation to C? Do you have a numerical approximation to C3? K3 is well known, but for C3,
C3 is known. We have a formula for C3. I didn't work what it. It depends on some Euler product, and it looks like it is perfectly known for many sequences. And in fact, this kind of sum go back to Erdős in the 50s. He already found some result about sum of two of many sequences, especially polynomials. But for the prime, it was unexpected to have a known formula. But you see with these examples that on the divisor side, we know much more things about sequences than on the prime side. So we can generalize. If we consider another type of sequence like u of k squared plus 1, which is related to Landau force problem, and we don't know if there are infinitely many primes in this sequence. But like for the Titchmarsh divisor problem, we know something on the divisor side. On Uli, Maki, Erdos before them show that SU of n is asymptotic to C for a constant n time log n. I think here the constant is very simple. It should be depending on pi. It should depend on pi. On the prime side, we have another big conjecture, bigger than Hardy-Littlewood, which is from Bateman on. And we can show that using this conjecture that the big pi sub u of n is asymptotic to K4 over log n. So again, we have a correspondence in the asymptotic up to a multiplier, which is a constant. So this led me to a second conjecture, which I call a stable continuity conjecture for admissible sequences corresponding to stable configuration, like polynomial, shifted primes. There exists a constant L, strictly positive, it's important, such that big pi u of n is asymptotic to L times R sub u of n. If L is equal to 1, it is balanced. It is the case of the integers in arithmetic progression, quadratic residue, etc. If L is not equal to 1, I call it stable, because you have some bias. You have a bias on the divisor side, and a bias on the P side, the prime side, sorry. So, in general, the pattern is, I test many sequences and the pattern is respected. I didn't find counterexample to this kind of correspondence, assuming that the sequence has no obstruction, is regular, and also has a polynomial growth. But now we can also consider set of integers, not sequences. So it is there are sets with a cardinality going to infinity, and this with this ID we can check something like the Goldbach conjecture. So the third conjecture in this talk is related to this kind of sequences, set of sequences of integers, and I call oscillatory continuity conjecture, because you will see that you have some oscillatory phenomenon due to a product on n. So for instance, if we examine the family big N minus P, where P is prime, and we let n be an even number, 2 times n, the length of un is pi of n. On the divisor side, we can also prove, like for Titchmarsh and others, we have something. On the prime side, we have some conjecture of Hardy-Littlewood on the prime count of the number of pair of primes leading to 2n is conjecture to follow this asymptotic. So if we come back to my framework, we have big pi of n asymptotic to omega of n, where omega is a abundant sequence times the divisor ratio. So W of n oscillates, but is rigorously bounded, considering the conjecture of Hardy-Littlewood on the what we know about the ratio, the divisor mass. Sorry. And we have a plot of Wn for Goldbach. You see it is clearly bounded, strictly positive, and it clearly doesn't tend to 0. The lim half is strictly positive. It is important also because for the conjecture, if we consider another case before the conjecture, like these inhomogeneous squares, the family n plus k square with k between 1 of n, the divisor mass involves a parameter-dependent local factor, a new constant, which is none. From the prime side, we have Batman on still, which give another parameter-dependent singular series, k6 of n. And the ratio is bounded but oscillatory. It doesn't converge necessarily, but is oscillatory. I have a graphic. I don't know if you see well because the dots are very small, but it is clearly bounded. This led me to a third conjecture. For parameterized admissible families U of n of moderate growth, we have pi, the prime ratio asymptotic to Wn, bounded function, times the divisor ratio. And the Wn as a lim half strictly positive. It is important if you want to tackle problem like the infinity, because if I'm going back here, if you have infinitely many, if you have a prime here, n minus 2n minus p is prime, so you have a Goldbach decomposition. So it solves the problem if the lim half is strictly positive. The conjecture is for the set of number which are not sequences but look like sequences. So that was the first part of the talk, where we have formally some correspondence between asymptotic related to divisors and asymptotic related to primes, with sometimes at the beginning you see with arithmetic progression the perfect match, which suggests that you have some structural correspondence between divisors on primes. And this suggests that perhaps we could know something about this correspondence, able not to have exactly the asymptotic match, but something weaker, but enough to prove some infinitude of primes in given sequences. For instance, I suggest to consider the domination principle. Here I take k equal to 2, even without knowing some Wn, like for the Goldbach conjecture. We propose a weaker principle. If you take 2 times, if you remember at the beginning, I compare this fuzzy ID to compare the probability to avoid divisors to the probability to catch prime. If you make 2 draws to try to avoid divisor, since the probability are perhaps close, when n is large, you will have a domination of the prime side on the divisor side. Namely, here it will mean that big pi u of n is greater than r u of n square. So this means that p u of n over v is the cardinality of the set we consider, is bigger to v over s u of n square. And typically, SU is asymptotic to CV log V. So this means that pi u of n is bigger than V over log V square. We know that it's n to infinity. And this forces infinitely many primes in the sequence. So the heuristic consideration could perhaps lead to this kind of result. Of course, I have no result about that, no theorem, but I suggest that to understand better the link between this divisor heuristic and prime heuristic. We can go further because we can imagine more draws to try to avoid divisor in the tableau. For instance, for k large, k equal 3, but more than that. And this time we have more chance to have pi, the ratio of prime big pi sub u of n greater than r sub u of n power k. It's perhaps easier to obtain. And in this, but you will have a ratio like pi u of n greater than v over log v to the k, and we know that it always goes to infinity also. So you can have many more draw and try to have to have the infinitude of primes this way. Okay, so to remember in the talk what is proved on this, what is conjectured, we see that on the divisor side, many things are provable or unproved. Asymptotic for the divisor mass, including precise formula for the constant. It is with the Dirichlet divisor problem first, but also Titchmarsh for the primes, shifted prime sequences. On the Goldbach also divisor problem. But on the prime side, of course, the big conjecture are still there. The prime number theorem for arithmetic progression R theorem, and also for many sequences for which the correspondence match perfectly. We know the result for both sides, so it is proved. But for, of course, Hardy-Littlewood conjecture, Batman-Horn, on Goldbach, on related conjecture, they are still conjecture. But what I want to suggest is that there is perhaps something to study more deeply, and with the conjecture, my four conjecture give some heuristic goals to consistence with non-result in number theory, perhaps worth to be investigated. From the experimental side, I checked many sequences, on they all seems to be okay. With a caveat, we speak, we have some logarithms inside the formula, so experiments, you should be careful before having conclusion from experiments, but it's possible if you are clever and you take the logarithm factor into account. but the link is clear for me. We have, there is something. So takeaways from this talk could be that a simple divisor mass ratio predicts prime frequencies at first order. To answer Doron's first question about the Riemann hypothesis, we see that we are at this level of elementary result in number theory. The purpose is not to know better, to have some result towards the Riemann hypothesis or its generalization. We stay with the first factor, but we see that with the last conjecture about the domination conjecture, perhaps we could know something about the infinitude of primes within interesting sequence, like primes plus shifted primes, or the Landau problem, n square plus 1. That's open. So there are many references speaking about the result. I didn't speak a lot about this non-result, but in the literature we found many things about that. But curiously, there is no evident connection between divisors and primes theory. The two objects seem separate, and if you take some book, classic book in number theory, and you look at divisors, and you try to find some link between the divisor of prime, except the trivial prime has only one divisor itself on 1. There is no evident connection between the two worlds. So I think it's interesting to think about it. So I think I respect the timing, and thank you for your attention. Sorry for my English, and happy to take question if I can answer some of your questions.
Thank you for beautiful experimental talk. This is really experimental. This is very fitting for our seminar. So you did lots of computer experiments and you confirmed all these conjectures for many cases?
Yes, it's not conjecture. Often you have, for simple cases, you have the theoretical result is true on the divisor side, on the prime side. I will try to write it down in a future preprint where I will give more details. But in general, for other, I tried some sequence very bizarre, and here the experiment suggests it is true. So there is a place for experimental mathematics on this subject. Also, it's experimental, but also observational. If you remember the first slide, when you see the arithmetic tableau, you are fascinated by the organization of number in the tableau, and you see some visual aspects. And in the experiment, I think also there is the ability for the mathematician to see pattern, to not only to compute, but to see something. And here we have that's the observation which lead to a conjecture, ideas. And after you use the computer to try sequences, big sequences, other sets of number. And at the beginning, I didn't want to write something about it. If you consider only the prime number theorem, it's merely a coincidence. The logarithm often appears everywhere in arithmetic, the harmonic number, etc. But when you see that it works for arithmetic progression, prime in quadratic residue, cubic residues, and you have so many correspondence. And for the Goldbach conjecture, you have a new proxy to perhaps attack this kind of problem, or the twin primes. I think that it is worth to be investigated.
Thank you. And more questions to Benoit? Yeah, so in this case, I have yet another question. That you said that they have to be admissible. Did you try to run the conjecture if it's mildly non-admissible? For example, very slightly exponential growth?
Alors, the problem with exponential growth comes from the probability to be prime. It's 1 over log, of the sequence. So if you take 2 to the n, it's become 1 over n, 1 over n, and so
exponential is too much, but you
yes.
You define admissible. So I wonder if you have a counterexample of something that is almost admissible by the conjecture phase.
The question is, from the big conjecture of Hardy-Littlewood and Batman also have the problem of the sequence admissible. You have a big hypothesis of Schinzel, you know, which predicts that in every admissible sequences, polynomial sequences, you have infinitely many primes. But we know that the admissibility of the fact you have no obstruction in a sequence to be prime is a very hard problem to decide. But perhaps the divisor, the mass divisor, could explain that the sequence have many, infinitely many primes. Of course, if you take a sequence like 2 times n, it is not admissible because you have no primes in the sequence. But for some other sequence like prime plus 2, of course, it's difficult to know it is admissible. But perhaps the Titmarsh divisor problem could shed light about that. But it's a difficult question. I don't know if I answer your question, but
yeah, kind of.
Admissibility is very, very complicated.
Yeah, it's very deep. Thank you. Any more questions? Well, thanks so much to Benoit, and good night.
Thank you.
Thank you. And
thank you for your
please end this meeting. Bye-bye, everybody. See you next week. Thank you.
Thank you, Doron.